I've known Barry now for about 40 years. It goes back to the Stanford Linear Accelerator experiment when we were finishing up our experiments that have been widely accredited with discovering quarks. And he was running a parallel series of experiments at Fermilab using neutrinos to look inside protons and neutrons, and indeed confirmed that what we were seeing was quarks. So he was trained as a high-energy physicist, like me, a particle physicist, an atom smasher. And he was leading one of the major experiments at the superconducting supercollider in Texas when that was canceled in 1993. Of course, he went back to his job as a tenured full-time professor of physics at Caltech, but it made him available to become the project manager of the Laser Interferometric Gravity Wave Observatory, or LIGO. And I think that the facility, one of which is here in Washington, the other in Louisiana, would not have gotten built without his involvement. They really needed somebody with experience in managing projects with hundreds of millions of dollars at stake and hundreds of physicists and engineers involved, and he turned the trick and got it built. So I personally believe that this discovery he's going to talk about today would not have happened, at least not by now, without him. He was the founding director of the LIGO laboratory, and in 2005 left to become the director of the International Linear Collider Collaboration. He's a member of the National Academy of Sciences and the American Academy of Arts and Sciences, a fellow of the American Physical Society, and served as its president recently when I was on the council. So I give you Barry Barish talking about gravity's music.
So thank you, Michael. I've never been to Orcas Island before, so when Michael called me, I couldn't resist. Brought my wife, and we're having a great time, so thank you. Somebody asked me in the last day or two what the take-home message is going to be when I talk today. I hadn't thought about that, but it's easy. I think the take-home message that I have for all of you who have different levels of what you understand about science is that maybe you'll appreciate modern science a little more than when you walked in the door. So that's it. You don't have to absorb everything that I say. It's meant for all the levels of people here. So Einstein's only quote that I know of that has to do with gravity, which is really the central subject that I'm going to talk about today, is the one here. But maybe he missed that we can, love science. So anyway, he's central to the story that I'll tell, and I'm going to tell it kind of as a story. Starting first with the punchline, if you want, which is shown here. This is a trace from our experiment in two places. One, you'll see, I'm going to tell you all this so you don't have to absorb it quickly, but one in Louisiana, a place called Livingston, Louisiana, and just outside of Hanford, Washington. And the first thing to notice, the top two traces that are shown, I'll tell you just slightly what they are, but you'll learn a little bit more as I go along. Look like each other. So that's the first thing to kind of register, is that whatever we saw it in both places. And not only that, at essentially the same time, within 7 milliseconds of each other in time. So that's the first thing to record. The second is just looking at it qualitatively. You'll notice that on this side, when the traces start, they're pretty wide, and then they get narrower as they come up here. And this is time. So narrower means faster or higher frequency. So what's happening is that whatever we're seeing, which I'll try to explain to you, is increasing the frequency with time. The time isn't very much. If you can see the bottom trace, it's only about 1/10 of a second or so. So over 1/10 of a second, this increases in frequency and in amplitude. It's getting bigger. That's the so-called chirp signal, or the sound that I'm going to have a hard time making, but the sound of the and that's the sound that we get. It isn't sound, but it's that kind of thing, and I'll try to explain to you. The little trace, if you can see it, that goes through the tube is the calculations that we make today from Einstein's theory of general relativity. And you'll see they go right through it, and that's the purification that I'm going to show you. And the bottom trace, the very bottom one, is just taking what was seen in Louisiana, what was seen in Hanford, and sliding them in time, and they follow right on top of each other if they slid by 6.9 milliseconds. So that's it. What did that come from? What were we seeing? And I'll explain the slide a little bit more. But we know enough now to know that it came from what I'm going to show you here. And, or at least that's what we are interpreting it as. This is a picture of something that occurred 1.3 billion years ago. So first, 1.3 billion years ago on Earth, we were just making the transition from single-cell life to multi-cell life. So that's when this occurred. It was 1.3 billion years, light years away, so the signal just got to us now. It's a long ways away. So that's what the 1.3 billion light years are. The two black objects are two black holes, what we call black holes. So what's a black hole? I'm not going to tell you in great detail, but a black hole is a region of space. In this case, the size of these isn't much bigger than the San Juan Islands, 50 kilometers across, which is a little bigger, but not much. Each one of them is about 50 kilometers across, and has a mass that's 30 times, roughly, the mass of our sun. So crowded into this space. So what happens in a black hole, it's very complicated mathematically, and we study it in detail, but it comes from, for example, a collapse of a big star, where the mass gets concentrated in such a small space that the gravity is so strong that nothing will get back out of it. And that's why we call it a black hole. So the gravity is just simply a lot of mass concentrated in an incredibly small area, 30 times the mass of our sun, not the Earth, in an area not much bigger than the San Juan Islands. So you can imagine the gravitational pull is enormous, and nothing that goes in can come out. And so that's why they call it a black hole. It's, of course, a little more sophisticated mathematically, but that's what it is. Actually, 100 years ago, it was really 100 years ago that both black holes by a man named Schwarzschild and general relativity, which is the other thing we need today, were discovered or proposed by Schwarzschild for black holes and by Einstein for general relativity. So what I'm going to show next is this video, and that's what happens when these two black holes go around each other. They're about 300 kilometers or a couple hundred miles apart. They're spiraling in each other, giving away energy in the form of what we call gravitational waves. And they spiral in finally into one object, which is what I'll show you at the end. And then it shakes a little bit. And that's a ringing down of kind of everything that existed. And then we will have one bigger black hole. That's what we say we observed. The picture you saw, this picture wasn't an animation. It's actually a computer-drawn graphic of the fit you saw on the very first slide. So when we looked at the fit and used the general equations of general relativity, and they just made it into a picture, that's the picture you saw. Okay, I'm going to go back in time now. Not back 1.3 billion years, but back to first at 1687. I think almost anyone in this audience learned something about gravity when you were in high school or elementary school or somewhere. And you learned that when the apple falls out of the tree, the Earth pulls it down, or when you jump up, the Earth pulls you down, was presumably what gravity is. That came from a theory that was developed by one of the greatest scientists of all time, Sir Isaac Newton, and he wrote it up in something called the Principia in 1687. What he did was basically understand this picture here, but what he did is understand somehow that whether it's the apple falling out of the tree, coming into the Earth, or the moon going around the Earth, or the Earth around the sun is the same effect, and it's all described by this equation. So the features of the equation, and he actually took some doing, because the major feature of this equation that I'm showing here is that the force of gravity falls quickly as the square of the distance away. So it goes as 1 over the square of the distance away. And what he proved mathematically was that if something falls as 1 over r squared, the force, that you get captured in these elliptical orbits, like the moon around the sun, moon around the Earth, or this. So otherwise it could just be not captured. So that was the idea that he had. He also did the detailed calculus to show that if you integrate over this whole mass, you can just assume it all happens at the center. This all happens at the center, so just this distance here. He also determined that the force itself was proportional to the masses, or the product of the masses. What he didn't do was determine what this factor was in front, which is how strong gravity is. And that he didn't determine. It was determined later, and I'll show you how in a second. So he determined this, and it basically was the equations. But you'll note that I never said in what he said, and he never said what it is that's pulling you when the Earth pulls on you. And we have to come back to it. So it was very much phenomenological. You got an equation, a set of rules that justify what gravity does, but it doesn't tell you what gravity is. So that's basically what Newton said. And then, so he called it universal gravity. That's what it's, if you see any books, universal means it applies the same for the apple as it does for the moon going around the Earth. Okay, then 100 years later, it took 100 years, a man, I'm not going to say this in detail, a man named Henry Cavendish actually determined what this factor was in front. That's how strong gravity is. In a very clever experiment. It's called a torsion experiment. And in this torsion experiment, he determined it. I'm not going to describe it in detail, but it's basically you twist this rod, and it tries to restore itself because it comes like a spring. And you can reduce that by having some masses on the end that you bring up close and see what it is. Very difficult experiment at the time. And he measured the strength, that big G. And it's amazing because he measured it almost as well as we know it today, a couple hundred years ago. This is the number in some units that we do. And this is the number which has a lot more digits to it that we have in the best measurements done today. And they're done in the same way, a torsion balance that he did. So that's all great, and we knew a lot about gravity. So this was a tremendous advance, and was used for everything that you can imagine where gravity comes into the picture. For example, describing the tides that we have, and almost anywhere else that we use gravity. So it was a tremendous success. And using it, the next important person was Urbain Le Verrier. He was a French mathematician, and he was basically the father and the person who basically developed what's called celestial mechanics. That is, understanding where all the planets go and stars around each other and all the forces using Kepler and Newton's theories. So he actually became famous because he did an observation that was pretty fantastic at the time. He basically predicted the existence of the planet Neptune. He did that by looking at the discrepancies in the orbit of another planet, Uranus. And by looking at the discrepancies in that orbit, he assumed that there was another planet that we hadn't seen yet, that was Neptune. And if you put in this planet in the right place, it accounted for all this difference in the orbit from what would have been there anyway. He then predicted that not only that the planet was there, but he had a certain drama, because what he did was determine where it was going to be, wrote a letter to an astronomer in Berlin, took into account the fact that it was going to take 5 days for the letter to get there, and told the astronomer where to look up in the sky. And within a degree, he found Neptune. So he became kind of the father of celestial mechanics. And he did the thing, so he did that. And then he, in the 1850s, discovered a problem that's often ascribed as why Einstein developed the theory that he did of general relativity, which, when I tell you the story, isn't quite true, I think wouldn't have been anyway. And that is, because he had this great success, he decided to use it for another problem that he figured out. He saw that Mercury's orbit around the sun, which is a very elliptical orbit, like shown here, every time it goes around the sun and comes closest to the sun, it's perturbed by the positions of all the planets, and it goes back to a slightly different position. So you can calculate using Newton's theory how far this moves, basically. And when you do that, you don't get quite the right answer. So using Newton's theory, you get almost the right answer, but not quite. I wrote down the numbers here. How far it moves was in units that I use here, arc seconds. 532 by Newton's theory, and 575 in reality. And that difference was real. People had measured it well enough. So he, of course, ascribed this, as he would, knowing his history, to the existence of something else that we hadn't observed. So Verrier predicted that there'd be somehow, Mercury's the planet closest to the sun, and that somehow we're missing some other object or objects that were even closer to the sun, and that was perturbing the orbit of Mercury a little bit, and we got this measurement. That was his idea. He gave it a name, Vulcan, and people started looking for it, and there were all kinds of what might be described as false discoveries. So there's a whole history of people saying that they had seen Vulcan, but they hadn't. And so by the time Einstein came along, this was still a puzzle, kind of. It hadn't been found, but maybe they hadn't looked well enough, especially if it wasn't really a planet, maybe a whole bunch of small asteroids. They even looked for this later in a NASA mission called Stereo, and proved that there weren't any objects larger than something like 5 or 6, I don't remember, kilometers in size, so not very big. And they basically then ruled it out, but of course that's after Einstein. So it was reinvented for television, movies, in Star Trek. So Star Trek reinvented Vulcan, but I'll point out that they reinvented it and put it 10 light years away, so it's not quite the same thing. So then Einstein came along, and he had, in 1905, solved 3 of the biggest problems in any given time in a subject like physics or mathematics. There's kind of the top problems that people can't solve or haven't solved. And Einstein came along, and so for physicists, it was amazing. He published 3 articles in 3 months in 1905 on different subjects that solved 3 of the top 10 problems, out of the top 10 problems that we had. One of them was the theory of special relativity, which people have heard about, of course, which is nothing can go faster than the speed of light. Things get more massive as they get heavy, and you have to look in a relative frames of reference, how you look at it. And he did that in 1905. Then he worked for 10 years. So this is a guy that went boom, boom, boom. And then he worked for 10 years with no results published. Maybe there was something, but nothing important. And he came out with a new theory in 1915. So 10 years it took him to do this. It wasn't clearly motivated by what I showed you before, because that wasn't important enough. He really did this from pencil and paper. So somehow had a vision. What he did was include acceleration and not just velocity in basically the theory that he had developed, special relativity. When you put in acceleration, it's a much more complicated problem. In order to solve that problem, he unified space and time. It becomes 4 dimensions, that we have this space dimension, that dimension in time, and they're all intermixed. in the theory. So it's one word. So for a physicist, we write down space-time. That's still not recognized by Bill Gates because when I type it on my Microsoft Word, it gives a little baby line. So anyway, when he developed this theory, which I'm going to talk about just a little bit, forget the formulas, they're just for looks. When he developed this theory, he immediately used it, of course, to recalculate the orbit of Mercury around the Sun, and he got the right answer. So he got the answer that is the right answer. And so rather than Vulcan, we now have a new theory of gravity after 250 years after Newton that gave the right answer for that. Again, as a scientist, explaining something that was a problem isn't enough to change to a new theory of whatever we're talking about. It's a necessary, but certainly not sufficient reason to change to a completely new theory of, say, gravity. Really, new theory should predict something we haven't seen before, not just fix a problem. Because you may be able to fix a problem in a lot of different ways, like Vulcan. And so it did predict something new. It actually predicted two things new. One that I'll talk about, which is our experiment. But the main thing that it predicted new was the bending, the formulas for the bending of light. So he not only predicted that light, now what the basis of this theory is in words, once you have a four-dimensional space-time, is that space and time interact with each other and do things like we use words like warpage of space-time. What it means is, looking at the picture here, is that if you think of maybe a simple picture of a trampoline and you put a big mass on it, the shape of the trampoline changes. And then if you throw a marble around it, somehow it has a different trajectory than if the central mass wasn't there. So that's the idea, that you change the space in a way that it changes, say, the Earth going around the Sun, because it's trapped basically in this warpage of space-time. That explains, you know, the different way of explaining the planets going around the Sun and so forth. The new thing is that it doesn't really matter once the Earth or the Sun warps space-time, whether the object that you shoot around it is a marble or a ball or something that doesn't have any mass at all. It's going to follow the path that you've created from the warpage that came from the presence of the Sun itself. So therefore, if we have light and it comes near the Sun, it'll get bent as it goes around the Sun, just as the Earth gets bent around in orbit. And so the way to test that is shown in this picture here, and that is if you take a full eclipse of the Sun and watch a star or some set of stars go behind it, you can watch as this moves closer whether the beam comes out to you even though it went behind the Sun. So he predicted it, he calculated how big the effect would be, and a physicist named Arthur Eddington made an expedition to the southern hemisphere to measure this effect when there was going to be a full eclipse of the Sun. This was 1919. So he predicted general relativity in 1915. He predicted this effect. And in 1919, there was an expedition led by Arthur Eddington. And he measured bending just as predicted by Einstein. And that actually hit newspapers all over the world, the bending of light, and it captured the imagination. It's what made Einstein a household name, not what we in physics attribute, which is what he did in 1905. So anyway, that all happened in 1919. In present day, you can, with an amateur telescope, if you're good enough, you can observe this effect of the bending of light by looking for something which we see called the Einstein Cross. And it basically is the what's called a quasar image that appears in 4 dots around a nearby galaxy. And if you look in the right way, you can see that. So many people have actually seen the effect of general relativity by seeing this effect. That's a little hard to do. Most of us don't have the best amateur telescopes. But all of you should believe that general relativity is right, at least in some form, because you use GPS. You may not know it, but GPS relies completely on general relativity. Why is that? We have these satellites that are up in the sky, four or more satellites, and we're basically taking the signal and measuring the time to get to you. And there's clocks on the satellites and in your little GPS receiver. And the first thing that's true is that what he predicted in 1905 affects it. The satellites are going fast. They're going roughly 24,000 miles an hour. And we have a little saying in special relativity, when you learn it so you understand which way it goes, that moving clocks tick more slowly. Okay? So a little bit, so somehow by having these things going 24,000 miles an hour, they're going to click more slowly. That's an effect that we have to take into account. And it is about 7 microseconds per day. But there's a bigger effect with the opposite sign that comes from general relativity. And that has to be taken into account also. And that is, if the satellites are that high, the amount of gravity that they feel is about a quarter of what it is on the Earth. If they feel a quarter of the gravity, then it turns out that using general relativity, the clocks tick faster, and that accounts for plus 45 microseconds a day. So altogether, we have a correction of 38 microseconds a day. So that just sounds like a number. So how does it matter? So 38 microseconds a day has to be compared with how accurate do we have to be with GPS to stay on the road. Okay. The accuracy is about 30 nanoseconds per day to have, say, 10-meter resolution. 10 meters is a pretty good sized road. And so to stay on a 10-meter, pretty fat road, we have to have 30 nanoseconds a day. Since this drifts by 30 microseconds per day, it means within a couple minutes you're going to be off the road. So basically this correction is made in the satellites and taken into account in GPS, and we wouldn't be using GPS without general relativity. So that's at least one takeaway you should have today. That's not part of general relativity that I'm going to talk about, and it's not the most interesting part for a scientist. General relativity is true and we've tested it in other ways in laboratories in what we call the weak field limit, where things aren't really changed very much, clocks a little bit, but not very much. Where we care most as scientists is when the gravitational field gets very, very strong. And in that case, Einstein's theory of general relativity might be right, or maybe some alternate one, or maybe something else, because what we know is that we have this whole theory of general relativity, and it describes a lot about things going fast and relativistic astrophysics and so forth. But we also have a theory that Michael mentioned that we grew up with, which is quantum field theory that describes all the elementary particles. And these theories have never been brought together. And so by getting into a physical situation where maybe they have to be brought together, we'll be able to unravel why these two worlds, what the real theory is between the worlds of what's done in particle physics and what's done in the kind of thing that I'll be talking about the rest of the lecture today. And the best laboratory that we know for that is one where the gravitational fields are super strong. That's black holes. So that's why this discovery of black holes, not that we can do the test so well now, gives us the potential of a new laboratory where we can study the gravity in its strongest fields, and maybe not only test Einstein's theory, but get clues as to how to bring all the theories together. So anyway, we say then in our paper, in the newspapers, when we saw this effect that 100 years ago Albert Einstein predicted general relativity, predicted gravitational waves, and 100 years later we've seen it. We even say it in our paper, and the headlines make it seem like we're pretty slow. It took us 100 years to test and see what he saw. The real story is a little more complex than that. including Einstein Spark. So I'll tell you a little bit about that. 1 year after he had general relativity, which he did in 1915, he recognized that the detailed equations that he was writing down, he didn't have a detailed, really quantitative formulation yet of general relativity, but he had the general features. And he noticed that the equations had a very similarity to what we do for electricity and magnetism, electrodynamics, that the equations had similar form. And because they had similar form, he concluded that there must be, just like in we have electric motors, we have electricity, we have magnetism, but then we discovered there's electromagnetic waves, and we have radios and microwaves and everything else. In the same way, he then, by analogy, predicted there would be gravitational waves. And he did this in a paper in 1916, and as I said, we saw it in 2016. But it isn't quite that simple. The paper in 1916 was absolutely full of errors. Both errors of concept and errors mathematically. He wrote a second paper in 1918 where he fixed the mathematical error, the factor of 2, and he developed something that's really important for us experimentally, which is what is it that makes a gravitational wave. So what we call a quadrupole formula. For electricity and magnetism, we get waves by taking a charge or plus or minus charge and doing this. And for gravitational waves, we have to have 4 poles, and we do it by having something that rotates. So anyway, in 1918, he fixed the factor of 2 error, and he fixed the concept of how they're generated, but it still wasn't really a fully developed theory. If that were the end of the story, it would be very interesting, but it's not the end of the story. So that's what he did in 1918, but then he revisited the problem in 1936. So leaping forward 20 years. In 1933, Einstein left Germany and came to the US for obvious reasons. And he came to the US and he came to Princeton University, to a new institute at Princeton University called the Institute of Advanced Study. He had been at my institution, Caltech, twice before that, and there was a battle between the two places to attract him, but he ended up at Princeton. So he went to Princeton and he worked with the man next to him in this picture, Robertson, and another man named Podolsky, and they developed in 2 papers in 1934 and 1935, 2 very important papers, not quite like 1905, but one paper that has one of the biggest puzzles in quantum mechanics, and that's with Podolsky, and then he and Rosen developed what we now refer to, and we can't talk about it today, what we call wormholes, although we didn't talk about wormholes. And then in 1936, he and Rosen, who was from the Soviet Union, wrote a paper entitled, "Do Gravitational Waves Exist?" You can imagine that writing the paper that says, "Do gravitational waves exist?" implies something to most people. Why would he write this 20 years later? He had decided that they don't exist. And so he submitted this to our most prestigious journal in physics in the US, which is the Physical Review. The editor of Physical Review at that time was this man here, John Tate. He then took the paper and decided that this was a big enough deal that he sent it to an anonymous referee. The anonymous referee we know now, because we can go back and look at the records. Anonymous means you don't know. But now we've been back and looked at the records. I showed them down below from the Xerox of the logbook at Physical Review, which shows what happened in that paper in the second row. To this man here, Howard Percy Robertson. Howard Percy Robertson was also an expert in general relativity at Princeton, who happened to be on sabbatical at my institution at Caltech at the time. And he looked at the paper and he didn't like the fact that Einstein had tried to describe everything about space-time with, I'll be slightly technical, a single coordinate system. And this is very difficult to do. You have this 4-dimensional space. He used all of it, tried to solve it all in one formulation of space-time. And so Robertson reformulated it in what was called cylindrical coordinates, which is simpler. And the problems that made Einstein think that there were no gravitational waves disappeared. So he wrote back to a letter back to Tate as a referee and told him what he had found. And Tate wrote a really modest letter to Einstein, which I quote from here, that he'd be glad to have Einstein's reaction to the referee's comments and criticisms. Now, Einstein's reaction to that was this. And this is the letter that he wrote back to that physical review. He said, Mr. Rosen and I, Mr. Rosen had already gone back to the Soviet Union at that time, had sent you our manuscript for publication and had not authorized you to show it to your specialist before it is printed. I see no reason to address the, in any case erroneous, comments of your anonymous experts. On the basis of this incident, I prefer to publish the paper elsewhere. He did send it elsewhere, and he never published again in his life in Physical Review. So, now on his side, peer review, which was used in this particular case, was just coming to be. And all the papers until he came to Princeton that he ever published were published in German journals that probably didn't use peer review. So this may have been the first time he ever encountered peer review and didn't even know what it was about. Now it's completely common, and that's the way we do things as a check on what we do. So he submitted it to a different journal, a journal called at the Franklin Institute, which is the Franklin Institute, some people may know, in Philadelphia, that had a journal at that time. They don't anymore. And he sent it to the Franklin Institute, and at that time, it wasn't quite like now, that you can publish a paper in a microsecond by just putting it on the web. It had to be typeset and copy edited and blah, 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 so it took months, luckily for him, because during that interceding months, let me go back. During the interceding months, he basically was doing whatever he was doing, but Mr. Robertson came back from Caltech to Princeton and met his new assistant at that time. They had some conversations, and he showed this assistant what was wrong with the first formulation. The assistant went back to Einstein and showed him what was wrong. Einstein's reaction was, "Oh, I found that last night." And then he finally published the paper, and the name of the paper was just on gravitational waves, and had, the more advanced formulas and so forth. So that was Einstein's. This is then, if we change now toward this being an experimental subject, is a picture of what happens when these two objects get together, like I showed you before. They come together. This is gravitational waves then coming out into space, taking 1.3 billion years in this case to come to the Earth. Once they come through the Earth, their effect on the Earth, or an instrument on the Earth, is to distort space-time in a way that changes the shape of the body it goes through. So it changes the shape of the Earth as it goes through, and then gets faster and faster, kind of like I showed you that first trace. We try to do that then by looking at the effect in an instrument that I'm going to tell you how it works. But first, in a little video, I don't want to show that again. So let's move on. So the effect is to change space-time such that that the coordinates are changing up and down. You get distorted. So imagine that you go to an amusement park, and there's these mirrors. One mirror that makes you a little taller, and one mirror that's tall and thin, and one mirror that makes you short and fat, and you go back and forth between those. And so that's exactly what happens to you. That if a gravitational wave goes through you, it makes you taller and then shorter and fatter at the frequency of the gravitational wave. So if it's 10 times a second, it does it 10 times a second. But the effect is a little bit small. So and I'll tell you how small the effect is. So the idea is that that's what's happening in the coordinate system. And then we want to somehow find a way to detect that as an experimental problem. And we happen to have a device that's nominally very good at that, if you make it good enough, because it is much easier as a scientist to measure the difference between two things if they're the same effect than it is an absolute thing. So measuring the absolute size of a meter stick is very difficult. But measuring a small change that's a difference between two things can be easier. In this case, it's perfectly matched to what we call an interferometer. So this is an interferometer, which I'll describe to you now, which basically, you can think taller and is this way, shorter and fatter is this way, and it goes back and forth between one arm, the arm horizontally getting longer and shorter, and the arm vertically getting taller and thinner. So an interferometer, which is the device that I'll talk about, measures that by comparing light that comes from a laser, like the laser I'm holding. I'll show you, it's a little more complicated. Comes into a mirror, sends light this way and light this way, and if there's no change, light coming back from here and here come back at the same time, we then arrange it so they basically cancel each other. And in a detector that's sitting down here, we see nothing. But if one of these arms gets a little longer and the other one shorter, they no longer exactly cancel, and we see that as a signal. So that's the idea. And this is a picture of it, and the way we do it, and I'll show you the graphic again a little bit more so you get the idea. So a laser comes in, we split the beam half this way, half that way, trap it between, these are mirrors and free masses. The way we make them free masses, they can be moved by the gravitational wave that goes through, is hang them from wires. So basically hung, and we're basically measuring this getting longer while this gets shorter and vice versa, and by them not canceling as they come through here. And I have a little video to demonstrate that. But first, let's go back to the effect itself and how much we have to measure. So the effect I can calculate now by looking at what we saw. So what we saw, I told you, were 30 solar masses, 30 times the mass of our sun. The size of them was about 100 kilometers, and the frequency that we saw on that graph was about 100 hertz. And the distance away was about 1.3 billion light years, which is in the unit that we talk about, megaparsecs, 500 megaparsecs. And these units are going around each other. So if we take all that, I can calculate the strength of this signal, and therefore the distortion of space-time. And it comes out in these units. The thing to pay attention to here isn't the formula, I just write it down for completeness, but what we measured, I wrote down the formula for how much longer over how long it is. We can measure, and it's 1 part in 10 to the 21. This is a lot of zeros, so it's an incredibly small effect. But we have to measure the fact that in one direction it got longer, and the other one shorter, by 1 part in 10 to the 21. So let me remind you how small that is, so you can just get an appreciation of what it takes to actually, even though the concept is maybe easy to understand, but to actually do this, what it takes. So we all know what a meter is. How about a human hair? A human hair is 100 microns, and it's 10,000 times smaller than a meter. So, okay, we can all conceive of that. What about the wavelength of light, like this light? It's about 100 times smaller than human hair, so the wavelength of this light is 100 times smaller yet. The atomic diameter, it's a factor of 10,000 times smaller than the wavelength of this light. So we're going down another factor of 10,000. Notice these are all multiplying, smaller and smaller and smaller. But we're down to atomic sizes. Then if we go down to the size of the elementary objects, the proton, it's 100,000 times smaller than the size of an atom. And it's 10 to the minus 15 meters. If we take then the length of the device that we're using, which is about 4,000 meters long, then we have to measure something that's about 10,000 times smaller than that. So we're trying to measure a change of length that's 10,000 times smaller than the size of a proton. So you can all disbelieve everything now. So the idea, showing you an animation, is shown here. And it's what I said before. If the light goes through and they're the same length, then nothing happens. But if they change, then you see a light coming through. And this is just showing up with real waves, which is what light is. And so you can see as light comes in, we split it in the two directions. It comes off of the object that we're seeing, whether it moves. They come back. If they're at the same time, nothing comes through, or they come through in phase or out of phase. They come back the same or out of phase. And as they change, as you'll see in a minute, being in phase or out of phase, that changes. You notice whether it's colored here, whether any light is coming to the detector. And that's basically the way what we measure. We measure it in two detectors. And those two detectors are 3,000 kilometers apart. They're in a rural part of Louisiana, a place called Livingston, Louisiana, which is about, I don't know, 50 miles or so north of New Orleans and a little west. And just outside of Hanford, Washington, on the DOE reservation there. They're 3,000 kilometers apart. It takes 10 milliseconds for light to go 3,000 kilometers. So if we have something that's detected here and detected here, if it came this direction, it would be here 10 milliseconds before here. If it came this way, it would be 10 milliseconds earlier here than here. And if it came in the middle, they would happen at the same time. The event that I showed you was 7 milliseconds earlier here than here, and that gives us some idea where it came from. Not very well, but some idea where it came from. And that has been kind of a bragging thing for the staff that works in Livingston. I think they saw it first. But that's a very important thing for us in terms of planning. They have to be no more than 10 milliseconds difference in time, or it can't be the same thing that's being seen. So that's what we look at. The devices themselves look like this. This is Hanford, Washington. And as you probably know, that when you go that far east in Washington, it's kind of high desert. So this is pretty stable, high desert, not much water. And we built one instrument there. The second one, which is in Livingston, Louisiana, is a rather different geology. It's commercial pine forest. If you notice along the side here, this is water. The water table in that part of Louisiana is maybe an inch below the surface. And so basically we built the device up over what's called a 500-year floodplain to get high enough, same way they do a highway. But we had to get the dirt from somewhere. So the dirt came from this borrow pit along here, which immediately filled up with water, and then fish and alligators, truly. And then the hunters came and shot the alligators, and we had various things, so it's exciting. Anyway, these two instruments are key to doing the measurement. Now I'm going to show you a few results which are a little bit technical. So first, what's shown here is the frequency that we look at. Right? So we talked about the frequency of the gravitational wave at the very beginning. And what's accessible to us is where our laboratory is the Earth. And so the question is, where is the Earth quiet enough that we can make this great accurate measurement? And it's basically the audio band. Which is the same band, it's the same reason. By evolution, our ears have figured out where it's quiet. If we heard sound at lower frequency, then our ears cut off. The Earth vibrates like mad, so it would be too noisy. So our ears have learned to not have that noise. And at the very highest frequencies, our ears cut off because you can't sample fast enough, so you can't hear the sound. It's exactly the same thing, only we're not talking about an audio signal. We're talking about a different kind of signal, which is this change of length. But the quietness is what limits us again. So in our case, we are limited by the low frequencies, which is down here, tens of hertz, by the shaking of the Earth, and how will we manage to isolate ourselves from the shaking of the Earth. And at the highest frequencies, we're again limited just by light the ear, but in this case, by how much light happens from our laser in a shorter and shorter and shorter amount of time to go to the higher frequencies. And so we cover the same frequency band as the audio band. So people get mixed up a little bit and think we actually heard something. But that's because it's very easy for us to change it to an audio signal to just think about it and look at it. This is our sensitivity on that plot. And what to look at here is this is a log scale, and on the left is the same units that I talked about before, 10 to the minus 21, 10 to the minus 22. So if I want to see something at 10 to the minus 21, my sensitivity has to be well below that, or 10 to the minus 22. These things that come up, so this is the sensitivity that we used when we made this measurement. This is where we were a few years ago, and this is where we'll be a few years from now. What we put in just by making it work better. So we know we're going to be better than we already are in making this measurement. And in fact, between the old time and now, the improvement that we had was greatest at low frequencies, which is the reason we were able to make this particular measurement, which I'm going to show you because it happens at low frequencies. Those little graphs-like things that stick up happen in anything that whether it's this table or anything else, as natural frequencies in it. So if you build an apparatus and you put it on a table, that table has some frequencies that it likes more than others, and we are sensitive enough to basically be plagued by all those. Or the wires that come down, the shape of the wire, and so forth. We know all those. They look funny on this plot, but we just notch them out, and it doesn't affect anything. They're there all the time. So here's just some quick pictures of what the detector looks like. This is the laser, so it's a little bit more complicated than the one I'm holding in my hand. Actually, a lot more complicated because we need a laser that's not only, we think of a laser as, this is very green, it's one frequency, but the laser for us has to be much more stabilized in terms of its wavelength, in terms of its amplitude than this. So we have all kinds of tricks in order to make a very, very, very stable and powerful laser. So that's our laser, which we've developed and built, in this case, in Germany. And done it in a way with industry, so that industries build it so we don't spend all our time, which is what happens in our laboratories when we build our own things. We're not very professional, so this way it just works and we don't have to fix it. Second thing is those masses or mirrors that I refer to, which is what moves from the gravitational waves. They're a great big piece of glass made out of fused silica. This is a picture of those. And the surface of it is as good as the very best telescopes that are made, as well as we can possibly make the surface, so that we don't have any difference in path lengths. And then they're coated with a coating, 10 layers, very thin layers of a dielectric coating that reflects light at the wavelength of the laser, which isn't this wavelength, but it's in green, it's way outside the visible band. It's 1024 nanometers, which is very deep infrared. And but to the eye, these look like just a piece of glass. You just look through it, and it's just a beautiful, beautiful piece of glass. They're big and heavy, because we want big, heavy test masses to be moved by the gravitational waves. And each of these hang by wires, as you can see kind of here. So the test mass that I just showed you hangs here, and it's hung by wires, and above it is all the controls. We want to keep the controls away from the test mass so that there's no noise introduced. And it's a hard problem because we have a quadruple test pendulum where we're trying to control the position of the very bottom one by moving the top ones. And those are our test masses. And then the thing that enabled, the single thing that enabled the measurement that we just made is shown here, but it's very hidden, but I'll describe it to you. What we have to do, as I said before, is to isolate ourselves from the ground. The way we've done that until this last year was purely by making the best set of shock absorbers like you have in your car that you can imagine. Very carefully chosen springs with dampers in them and just making the mechanics as good as you could possibly make it. We spent about 10 years developing a system which would be active and not just passive isolation from the ground. That's the system that enabled this measurement. What it is basically equivalent to these noise reduction earphones that you use that see ambient noise and cancel it. But in our case, the problem is harder and smaller. We basically want to take care of any motion of the ground in this direction, this direction, this direction, the rotational directions. And so it's 6-dimensional. And basically, we want to make sure that if we correct in this dimension, it doesn't screw something up in this one. We install this thing, and if you look down, it's all, in Louisiana, it's all water. Hanford, it's sand. Look up, it's sky. So it's asymmetrical, however you do it. So we have to understand very much the different adjustments for the 6-dimensional system, and it has to be very, very fine, you see, very tiny adjustments. This technology has been developed with industry and it will be big improvements for industrially for people who make microelectronics, if they can afford the tables, because you can make very, very stable tables this way. So that's basically the technology, just to give you a sense of it. And this is the signal that I showed. So the signal was the one that I showed here, and if I instead plot frequency, which is up, and amplitude being how bright the signal is, you can draw a picture like this from these signals here. So now I'm going to show a little bit of results, slightly technical, but for the people that understand this better, they'll understand this. So this is what happened is we turned on for the first time with the improved detector last September. And at that time we had the active seismic system in and the new laser and all this kind of stuff. Not working as well as they will in a few years, but working pretty well. And the very last thing we do is to test that nobody wants to change anything once we run. So we have a very last thing, which we call an engineering run, but it's not engineering because we're not doing engineering. It's the last write-off that nobody wants to tamper with anything after we start taking data. And during that time, we saw this event, which I showed you already, and I'll describe it now. And then, how do you determine whether it's real or not? That's the next question. So we saw this thing, and then to us it looked real. Of course, it's what we're looking for, but how do you actually quantify that? We quantify it by taking and comparing what we saw in two bins where it was the same time within 10 milliseconds of each other in Hanford, Washington, and Livingston, Louisiana, and then just move to a different time bin in each where it's out of time with each other and see what's there. And what we get is the curves, the data here. This is a log scale, so 10 to the 0 means 1. So this is the event. And this is the significance of the event. This way, I don't have to define it for you, but the significance was here. And the further out you are this way, the better. And basically, this was the second best event, third best event, but this is the one I'm going to talk about. This is the analysis of all those side bins compared with each other. When you're out of time by 10 milliseconds in Washington compared to Louisiana, 20, 30, 40, 50, and we just did this for 1 month of data. And we got this curve here. So there was no other time, no other coincidence we could make during 1 month of running that gave anything as significant as this. And in fact, even these were false, in the sense that if we remove the event itself, this is what you get. So this is stuff out here is all the real event in one of the detectors against random stuff in the other one. So this was evidence for us doing it more quantitatively, that the actual probability that this happened by accident was less than once every 270,000 years, which in physics terms is the magic number that we talk about, 5 sigma, which is a probability that's so small that we don't worry that it was an accident. So, what did we see? In this graph, I'll try to explain physically what we saw that was there. First, and when you saw this part of the curve, this is now the fit that comes from general relativity. So I'm not showing you raw data, but the best fit to the data. So they were wide and narrower and big. So at the beginning, they're going like this, like you saw in that first picture. They're getting closer together. They're merging in this region here. And finally, in this region down here, they're bringing down. So that very last thing, they were bringing down a little bit. More interesting, and so you probably understood that picture kind of, but more interesting is the bottom picture. And in the bottom picture, the thing to notice is the left-hand curve, left-hand scale. It's the velocity. It shows 0.2, 0.3, 0.4, 0.6. That's what fraction of the speed of light they're going. And this is how fast it's going as it's merging along here. So it gets up to a velocity that's over half the velocity of light. That doesn't come through very well in the video that I showed, but because that's been slowed down and it's the wrong scale, but to be out 100 kilometers, you have to realize not only do we have two objects that are each about 30 times the mass of the sun, each one about the size of the San Juan Islands, only separated by 200 miles or so, going around each other at more than half the speed of light. So that's pretty phenomenal. And this is just their separation getting closer and closer together until they merge. So that's physically what's happening. And so from that, we then can calculate, once we use Einstein's equations, we can calculate these parameters pretty well, actually fitting all this curve very well. And we know that one of the objects was 36 times the mass of the sun. The second one was 29 times the mass of the sun. And the final object was 62 times the mass of the sun. If you add these two up, it gives 65, and this is 62. The difference is that 3 times as much mass or energy as is in our sun was dissipated in 1/10 of a second. This is more than all the other energy in the universe during that period of time. And it all came off in the form of gravitational waves, which sound like maybe that should be easy to detect, but they're too high. It's a very weak force. So eventually that got to us, and we detected it. The other features are how far away it is. That's just we measure something called megaparsecs, but that's multiplied by 2 or so, and you get light years. And if they're spinning, we also know how that the spin of the final object, this starts to become important when we try to understand later the connections between quantum physics and gravitational radiation. This final black hole is spinning at 2/3 the maximum spin that it can possibly be at. And so it's spinning, it's not just sitting there, it's spinning very, very fast. And this is just what the curve looks like. We actually ran longer. I'm going to show you the rest, which we announced about a month ago. So what I've shown you is this InSpiral, which is the first event, which we announced February 11th, I think, of this year. We've seen 2 other strong candidates for events, one which we call an event, and the second one which we just call a candidate because we can't ascribe the 5 sigma to it. It's probably a gravitational wave from a black hole merger, and so I'll show it to you that way, but we don't declare it as an event. So these are the 3. And this one we just announced 3 weeks ago, so if we were making a mistake here, we've done it again, we've seen it again, so it's not, and we have one other candidate. So let me show you all of them together now, and you'll see where we are, which basically brings you up to date with where we are. This plot, I think, is kind of the most instructive, because it basically shows the first event, and the difference between how it happens. This is, you'll remember, is the same plot of our sensitivity. Anything that's above this line, we can measure. Above this line here, we can measure. So we don't see anything at these low frequencies where the sensitivity of the detector is not good enough, but once the sensitivity of the detector is better than the lines that come across, then we can detect them. So the first one, the one that I showed you, is the biggest one. That's the biggest signal we've seen. It goes up to here and then it dies off. The reason it dies off where it does is it's very heavy masses of black holes. The second one, and that's this one here, this is what you saw. It had about 10 spirals in it. The one we announced 3 weeks ago is this bottom one. And it has more than 100 spiral wiggles in it, but it's weaker, that's this here, and lighter, which means it goes to higher frequency. So we see it for longer, and we saw that for more than a minute, going like this detector. The middle one, which, as I say, we don't give it, this GW means we've declared it as a gravitational wave. This just means it's a trigger, and it's somewhere in between. But I'll show it to you in the plot. And it's a little weaker. The reason it's weaker is it's further away. It's about 2 billion light years away. And it comes up to about here. Its features look similar otherwise. So these are the other features, and kind of a preview of what will happen when we start getting many of these. First, this is the second event. So as I said, it has this really nice feature that it goes along for a long, long time, but it's not as big as the first one that we saw. So it has the ability for us to test a lot more things about this long oscillation, but the signal isn't as big, so we get better information in one sense and worse in others. The insets here are just how well we were able to, how well the Einstein formulas fit on those different regions. And again, on the bottom plot, you can see it gets up to more than half the speed of light. This is all these put on the same plot. So the left one here is the spin and the mass of the different objects. This is the first one we saw. The two circles are kind of the most likely mass and spin, and the next likely. This is the second one that's not an event, not declared an event. This is the third one. So you see we see different masses. This is the mass compared to the mass of our sun. So they go from 20 times the mass of our sun, which is already a lot, to about 62 times the mass of our sun. And in this direction is the spin of the black hole. And they're all spinning at about 70% of the maximum spin that an object like this can have. The next plot on the right is how far away these are, basically with our error of how well we can measure them. So we know the first two are about 1.3 billion light years away. Those are the two we declared. And the next one was more like more than 2 billion light years away, or 1,000 megaparsecs. So now I'm just going to give you a clue what all this means and why people get excited by it. So we've always thought that, and always learned that as we look at the universe in different ways, we've learned a lot more about the universe and kind of astrophysics. So the history of astronomy is that starting with Galileo, we looked at basically the optical part of the spectrum for hundreds of years. And the big advance the last 50 years is to look at do astronomy looking at different wavelengths, infrared, ultraviolet, and this has changed. And then you look at the same phenomenon in these different wavelengths. Going to gravitational waves, we of course are looking at a completely different way to look at the sky. It comes from a different mechanism. You want to combine the two eventually, and that's why we want to be able to point well in the end. But we've always felt that then if we, or believe that if we can look at the universe in a different way, like with gravity, we're going to see things differently than in astronomy. And so with all the hundreds of years of astronomy that's been done, with one single event, we already saw something that was quite different. And that is these heavy black holes. So the first thing we learned that wasn't known before is that there are what we call stellar black holes. These came from the collapse of the star. They've only been inferred indirectly. We saw them interact with each other. Second thing is that they form themselves into pairs going around each other, just like the Earth around the Sun. Or, maybe there's even just binary pairs, maybe there's threes and stuff, but at least they form in pairs within the lifetime of our universe. And within the lifetime of the universe, they even merge and send off gravitational waves. So that's all new kind of qualitative information, but having to do with gravity. But the thing that's completely new from the standpoint of astronomers and astronomy is that it wasn't even believed that there could be black holes that were this heavy. The reason is that big stars don't stay together very well. They kind of fall apart unless they're in a region that has no metals or heavy elements around them. And so it was believed that there weren't black holes, even though we had never seen black holes that were as heavy as 20 solar masses. And yet all of ours are. By inference, this is the heaviest black holes that were seen indirectly by X-ray studies. And here are our three events. This is the first one, 2 black holes here merged to make one here. Mass is this way on the scale, so this is heavier going up. This is the second one, and the one that I shaded somewhat darker is the one that we're not sure or don't declare quite as a black hole. But all of them, if you look at the final object are heavy compared to what was known from astrophysics. So what we want to do now is to get a large enough sample so we understand the population of these, how they originated, and what their features are. So that's understanding astrophysics. The second part of the problem for us is to understand basic physics with this new laboratory. And as I said, there's no better laboratory than to look at black holes to see the extreme case of studying gravity. So the first thing that we did was try to test general relativity. I'm not going to show you those tests, they're a little bit technical. Everything works so far at the level we're at, but we've only seen 1 or 2 events. Instead, what we can do is to ask, well, does gravity have a particle associated with it, just like particle physics does, called a graviton, which again starts uniting particle physics with general relativity, that is finite in mass. If it had finite mass, then all of the frequencies that it traveled at would be at the speed of light. Because once you have something that is finite mass, it doesn't go at the speed of light. That would change the shape of the thing we measured a little bit. And so we look at how much we can tolerate just from the measurements we made, a change of shape of that form. And with that, set a limit of 10 to the minus 22 electron volts on the mass of this empirical graviton. And so that basically is a first result from testing general relativity, if you want. So the future for us is to do both of those. So in a sense, we're a little bit like the birth of astronomy, only it's a new kind of astronomy. Galileo started doing astronomy in the 1600s, and basically it's developed for a few hundred years as a new science. We started this in 2016, and so what can we look forward to? First, the kind of objects that we saw here. So, coalescing binary systems. We had 2 black holes, that's what we saw, and we're going to study those. There's other objects that are compact objects called neutron stars. We thought that that would be the first observation we'd made. Most of us thought that would be true, at least I did. And so what we look forward to, maybe in the next running or soon, in addition to getting more information on the black hole mergers, is to look at binary neutron star systems, which are light, so they go out to very long frequency. They're very well matched to our device, because it covers the frequency range we're in. And maybe also black hole neutron star systems. So those are binary systems. There are other systems. So the second one is bursts. So what are bursts? If a star collapses, what happens in a star is it eventually burns up its fuel. It's a nuclear reaction, fusion reaction, that's making it burn, that's forcing the mass outward. In the meantime, gravity is trying to make it come in. It burns up the light elements, any star, including our own. Eventually, it gets old enough so it can't burn enough, and the star collapses. and that's called a supernova. And so if a star collapses, that's gravity. And so seeing the gravitational wave signal from the collapse of a star can give us a lot of information about the whole dynamics of what the collapses are, which we know very little about at the present time. People try to study it by big supercomputer programs to try to understand it. Another possible source of gravitational waves, and this is probably a ways away before we can do it, if we can in our experiment, because we work at such high frequency, is signals from the very earliest parts of the earliest times in the universe. And the earliest times in the universe, the gravitational wave signal, because I showed you it's so weak, goes back to essentially the Big Bang. What we study with photons, or electromagnetic radiation, is absorbed in the very early universe, so you can't get back to the very, very early times. So once these can be observed with gravitational waves, maybe not in our frequency band, maybe in lower ones or advanced versions of our detector, that'll be incredibly exciting because you can get back to very, very early times. And lastly, there's sources that are completely different. When a star collapses, it makes a final object, like a neutron star, and they spin. And those neutron stars are detected in radio telescopes, for example, or SIBO, different radio telescopes. And as long as they have some, what I called earlier, quadrupole moment, they'll emit gravitational radiation. And so that's another search object that we look for. So that's LIGO. But LIGO's not the whole story. So in LIGO, we're on the Earth's surface. The band that's available to us is the same as what I call the audio band. And that's physics or astronomy that happens on time scales of fractions of a second, milliseconds, time scales. If we go into space, then the kind of phenomenon that you can look for using gravitational waves is a different time scale. It's minutes to hours. So any phenomenon that takes minutes to hours, you can see in space. There's a mission called LISA, which was originally a joint NASA-LISA mission, a joint European-American mission. NASA pulled out, so it's now a European mission, but NASA's reconsidering it since our observation, so maybe they'll rejoin. This will go into space. They had a very good test mission recently, and it'll go into space about 10 or 15 years from now. And that'll see the whole different kind of physics, just like for astronomy going to a different wavelength, where we see things in the ultraviolet or the infrared. And then you can go to yet longer time scales. And people are trying to do that already in what are called pulsar timing arrays, measuring the time to get a reflected signal on a pulsar, from pulsars with timing. And lastly, by looking at the experiments that look at the very, very early universe. And maybe we can see that directly in LIGO or an advanced version at some time, but the way that will probably be done within a much shorter time is to see in the next generations of experiments that are looking at, in the electromagnetic spectrum, signals in the early universe. These are called cosmic microwave background experiments. When they get good enough, then you can see the imprint of gravitational waves that are left in the distributions that they see. An experiment thought they saw that a year or two ago. That was not, it hasn't held up, but I think it's not too far away when we can start to hope to see the imprint. The imprint is something we call polarization effects, which change the effect when you look over space. So that's that. I was going to play you music, but the audio is not working, so you're not going to hear this, unfortunately.